Hello, everybody, and welcome to electrochemistry. So today we're going to build up the ideas of electrochemical cells. But before we do that, we need to go ahead and go through a quick review of redox reactions. So redox reactions are really at the heart of most electrochemical processes. These essentially are going to be any kind of reaction where I move electrons from one atom to another. So a lot of our common organic reactions can in some degree be thought of as a redox reaction because electrons are moving from, say, an oxygen atom to a carbon atom or in reverse. However, a lot of the times when we think about redox reactions, we think about the classic electrochemical reactions, those that drive an electric charge when they occur. And so a good classic example is the lead acid battery. So a lead acid battery takes one solid lead electrode and one lead oxide electrodes, add sulfuric acid, and you generate lead sulfate. Now, one of the things that we have to watch out for when I have, say, a redox reaction like this is that they're a little bit more complex than the classic skeletal reaction might indicate. So often, in order to determine what's actually happening, we often need to split them into half reactions. So this happens by essentially splitting things into oxidation and reduction. So I know it's an old adage, but I usually like to go by oil rig and not Leo the lion. So in oil rig, oxidation reactions involve loss. Oxidation involves loss, and again, specifically here, we're talking about electrons. So I go from a high oxidation state, a low oxidation state like lead 0 to lead 2 plus. So my oxidation state is going up because I'm losing electrons as I go from neutral charge to positive 2 charge. And if something is oxidized, something else is reduced. So in this case, our reduction is going to involve a gain of electrons as I go from a lead 4 plus lead oxide to a lead 2 plus lead sulfate. And again, this is kind of a fun, if slightly unusual reaction because we end up with both reactions giving us the same final product. However, you may notice that all of these reactions are essentially skeletal in nature. They're focusing on the major species. However, one of the things we often have to watch out for is that most redox reactions are going to involve some degree of change in the solvent, which is typically considered to be water for most redox reactions. Let me know if you're interested in non-aqueous redox reactions because it is a very kind of special field. However, because we have a lot of charge moving around, it's also very common to see protons and hydroxide ions often moving in between cells and as critical parts of the reaction. So we'll also need to pay attention to these. So in practice, if I'm going to say try and balance my full lead acid battery, I'm going to have to do so by first balancing the half reactions and then combining them into my whole net reaction. And this is typically performed by going through a 7-step process. Step 1 is going to be to draw our half reactions and then balance any non-oxygen and hydrogen atoms. So in this case, it's going to be lead and sulfur. After that, we're going to balance the oxygen by adding water. And then we're going to balance the protons by adding protons. Then our charges are going to be usually wildly unbalanced by the protons we just added. So then we need to compensate by adding in electrons. And then to make sure the whole process itself is balanced, I have to make sure that both reactions share the same electron count. And this is typically going to be done by finding the least, the least common denominator. And then finally, we combine our reactions into the net reaction that we're after. And then, and only then, we often pay attention to the conditions, whether it's going to be acidic or basic conditions. If it's acidic conditions, we let our H plus hang around. If it's basic, we add in some hydroxide to cancel out any H plus, generate some extra water, and now I'm under basic conditions. So let's go ahead and do this example for our good old lead acid battery. So I can split my lead acid battery into my two half reactions. So first I have my oxidation reaction of lead, and then my reduction reaction of lead oxide. So in this case, they both have one sulfate, and so they'll both require one sulfuric acid. So then my next step is to look out for the oxygen. So in the um, lead case, I have four oxygens on the left, four oxygens on the right. I'm balanced. But on the second one, I've got six oxygens on the left and four on the right. So I need to add two waters to the right side to balance the system out. And again, this will occur in the liquid phase. So then I need to go ahead and balance my hydrogen atoms. So for the lead reaction, or so for my oxidation reaction, I have two hydrogen atoms on the left and none on the right. So I'm going to add two hydrogen atoms. And then for my reduction reaction, I have two hydrogen on the left and four on the right. So I need to add two protons on the left side. And you'll notice that at this point, we're starting to get a little bit messy. But wait, there's more. We need to balance the charges. For my oxidation reaction, I've got a +2 charge on the right side and 0 on the left. So I need to add negative charge to the right side to make it neutral. So I'll add 2 electrons to the right. And then similar for the reduction reactions, I need to add 2 electrons to the left. And then at this point, I get a freebie because I have the same number of electrons in both reactions. And you'll notice that this builds up to, well, quite some substantial uh, reaction terms. But now I know my system is moving 2 electrons per every mole of lead or lead oxide that is reacted. And so when I end up balancing this, we get a net reaction where I have lead plus lead oxide plus 2 hydrogen sulfates gives me 2 lead sulfates and 2 waters. So the biggest thing we learn here is a lot about the stoichiometry, and then keeping an eye out for the fact that we are indeed producing water, which is worth acknowledging. However, in practice, if I'm going to be running these redox reactions, I'm often going to want to try and measure how much energy is involved in one of these reactions, or in the classic case of a lead acid battery, I might actually want to be able to get some energy out of the system. So in order to try and capture this energy, we often split our 2-half reactions into cells, with our anode typically being placed on the left and our cathode typically being placed on the right. And in this process, we have electrons generated at the anode, because again, this is my reduction reaction, going over to the cathode, where the oxidation reaction then the reduction reaction proceeds to gain these electrons to complete the process. Now, I want to go ahead and walk through some of the key elements of this. So first of all, when trying to keep your anode and cathode straight, remember, vowels go with vowels, consonants go with consonants. So anode for oxidation, cathode for reduction. So in this case, we also are kind of lucky because we have lead sulfate on both sides. And this typically occurs in reality as lead sulfate precipitating out as a solid on top of our lead or lead oxide electrodes. And so what ends up happening here is I'm going to be pulling the lead sulfate or the hydrogen sulfate onto the lead surface, where we're then going to have an oxidation reaction, which then generates a buildup of electrons on the lead surface. So these electrons are going to want to go somewhere. So what I do is I go ahead and I connect a wire from my anode to my cathode, and I let the electrons essentially run through the system. And then in the middle, I'm essentially going to place some sort of load. This is essentially a term for whatever is essentially capturing the potential bias that's built up on these systems. Because one way of looking at it is, because my reduction reaction is consuming electrons on the cathode, I have low electron density on this lead oxide surface. And because my oxidation reaction is producing electrons, I have a buildup of electrons on this surface. So high density, low density of electrons. This generates what's called the potential bias. And that's what we can either measure with a voltameter or use to drive an electric motor, as the electrons are willing to give up some degree of energy in order to drive the process. The higher the potential bias, the more energy I can extract out of the electrons as they're passing through. One way to try and think about an electrochemical cell is a little bit like a mill pond. The higher up my mill pond is above my ending river, the more energy I can get out of the water as it essentially uh, falls past my wheel that will help drive the mill. And that's very much what happens in kind of an electrochemical sense. But if I'm letting negative charges move from the anode to the cathode, well, this would get me in a little bit of trouble if I just let it run as normal. So what we need to do is include a salt bridge, which then lets negative ions move to the left and positive ions to move to the right to essentially cancel out this movement of charges. So you'll often use, say, an actual salt like potassium nitrate. Potassium nitrate is considered a classic choice for a salt bridge because potassium and nitrate very rarely make complexes which can essentially mess with our electrochemical reactions. They're relatively electrochemically inert, which makes them a good salt, as opposed to something like sodium chloride, which may react with something like silver or lead to form a solid. So this essentially is how I actually run my reactions. However, there has to be a little bit more convenient way to demonstrate this full reaction setup rather than drawing out this full diagram, which I'm pretty sure nobody wants to wants to do on a computer. So instead, what we do is we make use of what's called line notation, where on my most left hand side, I'm going to go ahead and put my solid anode surface. And on the furthest right hand side, I'm going to go ahead and put my cathode surface. So I go from essentially lead sulfate mixture. And because these two solids are put together, we often will just denote them with a comma. But more traditional sources will say that the lead and lead sulfate are indeed in separate phases. So I should put a line here as well. And then in my solution, I'll go ahead and put everything that's in the aqueous phase. Usually I'm going to only focus in on species that are going to be relevant to the reaction. In this case, hydrogen sulfate and sulfate, as these will act as the concentrations of these ions will actually control the electrochemical potential, as we'll talk about later. And then I show a double line to represent my salt bridge as I go from my anodic cell to my cathodic cell. And then again, I repeat the same process. We start with the liquid phase, and then we move to the solid. You can also include extra lines if you have such phases, such as a gaseous phase, which is often seen for cells including, say, hydrogen or chlorine gas, where I have electrochemically active gas phase species. So next time, we're going to focus a little bit more on this potential side of the electrochemical cell, what it means, and what's its significance. Until then, take care.